Hello, good afternoon. My name is Somak Raychaudhury, and I'm continuing this series on gravitational waves at home with LIGO-India. I hope you're all keeping safe, maintaining social distance, staying at home, and are healthy. We are in this series making sure that we reach a lot of people all around the country and indeed around the world, and talking about gravitational waves, LIGO-India, and related physics. We talk about quite a wide range of topics. And in parallel, from IUCAA in Pune, we will also have several other series of such lectures and seminars that are being planned. Please keep your eye out for them. Today, I thought I'd talk about black holes because these are the major sources of gravitational waves as they are being discovered detected by the LIGO observatories in the US and the Virgo Observatory now in Europe. And these are the main sources, along with various other sources that I'll talk about, that we hope to detect when we are ready in India with LIGO-India, which the planned view of LIGO-India looks like this. Today, I'll talk about black holes and how they're observed in various ways. I start by Newton, as always, if you talk basically about gravitational physics. And I hope today to introduce the concept of black holes, first using Newtonian gravity, because it is easier to understand. It relates to what all of us study in school about gravitation in general. So Newton came up with this idea of gravity. As you know, when he was being quarantined, Cambridge University had closed for 1.5 years, very similar to a situation that we are in now. And he was in his early 20s, forcibly sent away by Cambridge University to his aunt's house, which had an apple orchard, where he sat and thought sitting under apple trees all day. I hope some of you will do so, even if you don't get apple trees near you. And he came up with this idea that he was thinking about why the Earth moves around the sun and the planets move around the sun. And he came up with this idea that the gravity itself is a universal force that acts between any two bodies in the universe. Doesn't matter what they are, as long as they have mass, which is another concept that he came up with. And so all our objects have gravity, and then they pull each other, just like any two objects here in my room, the sun and the earth, the moon and the earth, etc. And he came up also with a quantification for it. And it says that anything falls due to the act of gravity towards another object with an acceleration, which is due to this force, acceleration being force divided by mass, which is proportional to the masses of the two objects, and inversely proportional to the square of the distance between them. This is some of the basic stuff that we are taught in school. Now, from that, we get a concept of what is known as escape velocity. So, which means that because two things are pulling each other, we are on the Earth's surface because the Earth is pulling us towards the center of the Earth, and so we are stuck on the Earth's surface. Can we escape from it? A lot of people have come up with ideas of how to escape from this Earth. I mean, as a lot of children think that if they jump high enough, they can probably escape. We've seen rockets escape from the Earth, and it's all governed by this concept that the Earth's gravity pulls us, keeps us on to the Earth's surface, and there is a threshold velocity called the escape velocity, and you must achieve that at least if you have to escape from the gravity of the Earth and go away somewhere where the Earth's gravity does not act on you. And this is given by this very simple formula that, again, is a consequence of the formula that Newton wrote down under the apple tree. And that tells us that the escape velocity is given by this very simple formula, and it has the mass of the object that is pulling you, which is, for example, in this case, the Earth, and the radius of the Earth on which you're sitting. It's the distance between the center of the Earth and yourself. And for example, if you're throwing a projectile up, it might not be you, it could be throws a little stone up in the sky. It will come down eventually, it will go up, and if you throw it with higher velocities, it'll go further up. And if you exceed this escape velocity, it'll finally not come down at all, and that is known as the escape velocity. This is a simple concept that comes from Newtonian gravity that's again taught at school. So black holes we can understand from this notion of classical gravity, even though it's not strictly the whole story, because the whole picture of gravity is not described by the Newtonian concept. But this gives us the basic idea of how to understand black holes, and that is, what if the escape velocity of an object is so high that it is higher than the speed of light? We know that the maximum limit to which anything can be sped up to is the speed of light. And so if something has an escape velocity which is higher than the speed of light, and then nothing can escape from it. And that is basically the concept of a black hole, which comes from this idea of Newtonian gravity. And so even in Newton's time, a lot of people had already, after learning about Newton's concept of gravity, had thought about what if we had stars or planets which are massive enough or dense enough that the escape velocity is more than the speed of light, then nothing could escape from them. We can just try and understand this from this very formula by understanding what happens if, for example, you change some of these parameters. So, for example, if you have an object that is of the same radius, say the radius of the Earth, but you have more and more massive objects, so more and more massive planets, the density of the rock being increased, then you would find that even for the same radius, as you can see in this formula, even from the same radius, the escape velocity goes higher and higher and higher. And that is one way that you can make it high enough that it reaches the speed of light. So you can turn something into a black hole, keeping the same size by increasing its mass. But that's not a very practical way of doing things. In nature, things don't increase in mass with their radius being the same. Arbitrarily, it's a very difficult thing to do, a very contrived thing to do. A more natural thing to do is, if you take the same formula and keep mass the same, but now decrease the radius. And you can see, because the radius is in the denominator, this means that as the radius becomes smaller and smaller and smaller, the object gets denser and denser and denser. This escape velocity can go higher, even if the mass of the object stays the same, which means that this object has to collapse. This also means, very interestingly, that anything can be turned into a black hole if they're squeezed into a size that is small enough. So you and I can turn into a black hole if we can make ourselves small enough. We find a process by which we shrink to a very small radius. Now, how small is that small radius? Let's look at that. And in order to do that, we have to look at the basic physics of it. But just to give you some numbers now, to escape from the Earth, as we looked at the escape velocity, just from that formula, the escape from the Earth, we need about 11 kilometers per second, or 43,000 kilometers per hour. And you can see that that's not an easy speed to achieve, given the normal speeds of cars that we drive. And that is why we need to propel rockets which to higher and higher velocities. Even with the current launchers that we have in this country, we can't reach these velocities at one shot. There are tricks to achieve this kind of escape velocity by going to higher and higher altitudes and achieving the escape velocity that is local to a particular altitude. From the sun, if you're worried about the Earth escaping from the sun, you can see the sun's gravity is so strong that in order to escape from the sun, you need millions of kilometers per hour. And that's why our planet is trapped with the sun, which is great. We're not going to go along escape from our sun into the universe. So I just told you that in order to then achieve the escape velocity of the speed of light, how small do these objects need to be? And that, to work that out, one actually cannot use Newtonian gravity. Well, one has to use Einstein's modification of it, Einstein's generalization of it, which I'm going to talk about in a minute. And from that, we can get this particular relation, which is called the Schwarzschild Radius, which means that if you take some object and squeeze it into a size, which the radius of that is this particular quantity, a very simple quantity, 2gm over c squared, where c is the speed of light and m is the mass of the object, then you can achieve an escape velocity that is the same as the speed of light. And so you turn something into a black hole. Now you can see here, I give the quantities that correspond to the mass of the Earth. So if you can take the Earth and squeeze it to something that's less than a centimeter, then you can turn the Earth into a black hole. You often read about experiments that have gone wrong and have turned the Earth into a black hole. And you can see how difficult it is to actually contrive an experiment that will turn the Earth into something that's smaller than a marble. Similarly, to turn the sun into a black hole, we'll have to shrink the entire sun into something that's smaller than a small town with a radius of about 3 kilometers or so. And this is why it is so difficult to do so. But as you will see, in nature, in the universe, it is possible to turn stars into such compact objects. And this is what we learned in the early part of the last century. But in order to do that, we have to now move away from Newton's theory in order to fully understand how these things work. And what we have to do is to generalize it, because Newton's theory of gravity explains the kinds of things that I talked about, which is how the Earth moves around the sun and the moon moves around the Earth. And one can calculate these motions with very high levels of accuracy. Using Newton's gravity, we can also calculate the orbits of rockets that ISRO launches, for example, and to a great level of accuracy. But as soon as you get into a situation where the speeds that are necessary are very close to the speed of light, or the densities are such that you can get these escape velocities that are very big, then you need to go to a more generalized theory, which Einstein introduced. Einstein noticed some anomalies in the basic formulation of gravity in terms of how gravity works between two objects. And he moved away from this notion that gravity is a force which acts like an invisible thread that connects two objects, that one object pulls the other as if they're connected by a thread. Instead, Einstein moved into a different kind of formulation of gravity, where gravity is the manifestation of a very local phenomenon, and that is, if something has mass, what it does is that it modifies, it introduces a curvature locally in the space in which that body is embedded. So in the Einsteinian concept, space or space-time, as he called it, actually has a presence. In Newton's gravity, objects that are in the universe have a vacuum in between them. There's nothing in between them. Space as an entity does not exist. Einstein brought in the concept of space as an entity. And the fact that things are embedded in space means that if you're massive enough, then you curve the space around you. And as a result, the more massive an object is, the more curved space is around them. And then gravity is a manifestation of objects that are interacting with each other because the space around them is curved, which means that gravity is not a force, and things move along space following its curvature. It means also, and this is also a departure from Newton's gravity, that light bends as it moves along space. In Newton's gravity, light has no mass, so as it moves through space, it cannot bend, it moves, it is not affected by gravity. In Einstein's theory, space itself can be curved due to mass, and so light can bend. And in the next lecture that is coming up, you will hear Professor Kimbavi talk about the effects of the bending of light by space-time. I'm not going to talk about that today. So in Einstein's idea, for example, gravity is an effect of curved space-time. So here is the sun causing kind of space-time that is in this artist's rendition is shown as a curved thing around it, and you have the Earth, which is being pulled by the sun, not because of a Newtonian force, but because of the fact that locally it is trapped in this dent in space-time, and it goes around the sun because it follows a trajectory in which it is led by the nature or the curvature of space-time. And that actually is a far more general and more accurate description of gravity. And one can calculate a lot of things from this formulation, which shows up as departures from Newton's formulation once one makes very, very accurate measurements of the motions of the planets around the sun and the motions of various things that we see in the universe. So Einstein's theory has slowly been, throughout the last 100 years, since it came out in 1915, been shown to be very accurate because of various measurements that have been made to show the reality of the predictions of Einstein's theory. So we needed Einstein's theory of gravity to work out really very accurately in mathematical terms how space and time behaves around a gravitating object, around a massive object. This is very crucial to work out what a black hole is, because as soon as you get very close to a black hole, the speeds that are involved get very high, close to the speed of light. And so normal Newtonian formulation breaks down. So in order for us to mathematically understand what a black hole is, we had to wait till Einstein actually formulated his theory of space and time in the general theory of relativity. Within a year of Einstein's formulating this, a solution was found by Carl Schwarzschild, after whom I've already talked about the Schwarzschild radius, the size of a black hole, is named because he solved Einstein's equations in the case of a spherically symmetric universe of how the space-time would be around a body that is gravitating, and found that that the shape of trajectories around a gravitating object would be of a certain mathematical formula, and that is known as the Schwarzschild metric. He actually derived this within a few months of Einstein's formulation of the general theory of relativity. Sadly, he was killed in the First World War after he derived this formula, and Einstein helped to publish his work. We still remember Schwarzschild's contribution to this, and also wondered how much he would have done if he had continued to live after the First World War. This work of Einstein and Schwarzschild came out to the rest of the world as we neared the end of the First World War, and people started working on the general theory of relativity in the late 10s and early 20s. In the next lecture, you'll hear how the first validation of Einstein's theory came from Eddington's expedition to the solar eclipse in West Africa to show that light bends, which showed that Einstein was right in his formulation and things like that. But how would you turn this notion of the Schwarzschild metric, which shows how space-time behaves around a compact object, into finding out how you can create a black hole? I just told you it's not that it's not that easy at all to convert an object like me or you or the Earth or the sun into a black hole, because you have to shrink something down to a very small radius. And to do that, you have to then look at what Chandrasekhar did. Subramanian Chandrasekhar came up in the 1930s as a student going to the University of Cambridge, working on the idea of how a star evolves and applying the laws of quantum mechanics to stars for the first time, and finding what happens when a star ends its life and how things collapse and can form objects of very high density that can be called black holes. So Einstein's notion of space-time around a black hole then is such that the space-time is bent so much that in order for something to come out of that highly curved space-time, it would require a trajectory that is not possible even for light. And so you can see how Einstein's idea of curved space-time relates to the notion of escape velocity in Newton's theory. So according to Chandrasekhar, when stars die, this is another lecture that somebody else might give you. I'm not going to go into great detail, but what happens is that during the normal life of a star, it burns nuclear fuel in its core and converts hydrogen into helium and various other higher elements of the periodic table. But in the end, when a star's fuel is finished, it goes to a catastrophic way of ending its normal nuclear fusing life. And many of the stars end up exploding, leaving behind compact remnants. Chandrasekhar showed by his application of quantum mechanics to the basic physics of stars that if, for example, a star that is about a mass that is equal to the mass of our sun, then it will collapse at the end of its life into what is known as a white dwarf star. Our sun is going to go that way. If, for example, it is much more massive than 1.4 times the mass of the sun, it can result into a compact star after it explodes in what is known as neutron star. But if they are much more massive than our sun, for example, it might collapse to something that would be smaller than the Schwarzschild radius. And this is how Chandrasekhar related this idea of gravity to astrophysics, to show that in the universe there can be black holes. That's what a black hole looks like, because of course you can't see a picture. You can't take a picture of a black hole itself, because nothing comes out of a black hole. And we take pictures of things in the universe, images, because of light coming from the object. However, what happens is, because a black hole is an extremely dense object, it has effects of its gravity around in its surroundings, and that is why we can pick up images of the effect of a black hole on its surroundings, and that's how one observes black holes, which is the topic of today's talk. We know that there are 2 or 3 different types of black holes. We know that the black holes that are formed in the way that I just described, there are black holes that are a few times the mass of the sun, and these can go up, as we now know, from the LIGO observations, up to maybe 100 times the mass of the sun or even more. We know that at the center of each galaxy, there are black holes that are at least 1 million, if not and up to a few billion times the mass of our sun. These are formed in very different ways. And we are now, there are some people who believe that there are black holes that are intermediate mass black holes, which can be maybe 10 to the power 4 or 10 to the power 5 times the mass of the sun. But there's controversial evidence for this, and I'm not going to talk about that. In fact, I'm not going to talk about supermassive black holes either here, because I'm trying to concentrate in this particular presentation on the kinds of black holes that, that LIGO finds, and also we find through our modern observations using X-ray telescopes. We know recently, for example, in the last year, we discovered black holes. I just said black holes can't be imaged. Of course it can't be imaged, because light can't come out of the black part of the black hole. That's why it's called a black hole. But in the centers of galaxies, there are these supermassive black holes. And one saw this in the front pages of newspapers, the image of the surroundings of supermassive black hole. I just wanted to flag this. Somebody else will talk about this, I'm sure. I'm not going to talk about supermassive black holes in this particular, the rest of this talk. I'm going to talk about the stellar mass black holes, and I'm going to talk about 2 ways of finding them, and just look at, and for the rest of today's presentation, I'm going to compare the 2. So the first way I'm going to talk about is how you can find these black holes by the electromagnetic waves that are emitted from the surroundings of the black hole. Now, we know that light comes in forms of various kinds of radiation. The light that we see with our eyes come in a very small range of wavelength or energies, and these are called, this is called visible light, and that's in the middle of this whole spectrum. But then if the energy increases or the wavelength decreases, you can see that you can go to higher and higher energies, and so you can have ultraviolet, X-rays, gamma rays, etc. For lower energies, you can have infrared and radio waves. And the thing is that a lot of these kinds of waves are emitted by, or all of this is emitted by stars and galaxies out in the universe, but they don't come through our atmosphere, because the atmosphere is totally opaque to a lot of this range of wavelength. I'm talking of the kinds of light that we see with our eyes, and that comes through in here. But if you have energies that are much higher in the ultraviolet and X-rays, the atmosphere stops them, which is good for us, because it's not good for our skin. But for astronomers, it's not very good, because we can't see the X-rays that come from galaxies and stars and black holes. But then infrared, etc., they don't come through the atmosphere. So one of the ways that we can detect the gas that's falling into the black hole is that because it's very hot, they get heated to very high temperatures, and they emit X-rays, and so we need to detect X-rays from these sources. And in order to do that, we can't do it from telescopes that are on the Earth's surface. We have to go above the Earth's atmosphere, and so we have to build space-based telescopes. And one of the telescopes that has been very successful in detecting these compact objects that can be black holes is the Chandra Observatory, which was launched in 1999 by NASA. And it is a very interesting telescope, which actually images X-rays with the resolution very similar to the optical images taken by the Hubble Space Telescope. It has a very interesting orbit in order to escape the radiation belts around the Earth, which also cause the detectors on the Chandra Observatory to be affected. It has to go very far away, very, very far away, hundreds of thousands of kilometers away from the Earth. And it can observe only in this region when it's very far away from the Earth. And it's shut down when it comes very close to the Earth. It observes, it has a period of 64 hours, and it is built in a very special way. Now, X-rays. X-rays are extremely energetic rays, and they don't come to the atmosphere, which is why, of course, we have to observe them from space. But as you know, they are very difficult to image as well. They pass through everything. We know that it passes through flesh. It passes through objects that mirrors are made out of. And so normally, when we observe things with optical telescopes, we observe them by reflecting the light from mirrors. But an X-ray would pass through an optical mirror. And so the Chandra Observatory does that by not reflecting them directly from the surface of the mirror, but reflecting them at what is known as grazing incidence, which means that the X-rays are incident on the surface at a very, very small angle. And that is, and at very small angles, they don't pass through the surface. And that is because the wavelengths of the X-rays, nanometers, are comparable with the spacing between the atoms on surfaces. And that's why if they come straight perpendicular to the surface, they can pass through. But when they hit them at grazing incidence, the effective distance between the particles on the surface of the mirror they see is very small, and they can be deviated, reflected. So that is why the Chandra X-ray telescope is very long, and you can see the surfaces are very are such that the rays come at a very small angle. And here, for those of them who are technically minded, you can see the energy of the X-rays is a function of the grazing angle. And you can see that, for example, if the object is made up of something like gold, then the mirrors are made of gold, then you can probably X-ray energies go up to about 3 degrees or so from the surface, and then it's going to go right through. And so you have to have them hit the surface at very low energies and very low angles. And you can see this is how these X-rays that come into the nested mirrors of the Chandra X-ray telescope are focused to form these lovely images that we get from the Chandra telescope. And we can make images of X-rays coming from celestial sources. So what are we looking at? We're looking at sources of these X-rays, and they would be black holes or neutron stars. Here we're talking about black holes. How do they form? I told you that Chandrasekhar told us that at the end of the life, at the nuclear burning stage, black holes turn into compact objects. Most of the stars in our galaxy exist in binary systems. Stars often like to live with other stars, and so often a star would be bigger, one star would be big, one star would be small in terms of mass. And the way a star evolves is that massive stars evolve faster, and so one of these stars would evolve to burn its nuclear fuel much earlier than the other. And as it would finish its life, it can eject the outer layers of at the end of its life, its outer layers, and the inner bit will turn into a compact object, which could be, say, a black hole. Now, this particular incident of something exploding, one of the stars exploding, can disrupt the system completely. And so it can eject this companion star. If it's a very close system, sometimes this system survives. And what happens is that then the other star, which is now a normal star, and this is a black hole, this normal star would then start evolving with a longer time scale, and slowly its outer layers will have very weaker gravity, much weaker gravity than it was when it was a full compact star, and its mass will then be, the outer layers will be pulled by the black hole towards it. Now, all the mass that falls onto the black hole will not be able to directly go into the black hole at the same time, and it would have angular momentum. So this mass would swirl around the black hole and form a little disk around this black hole. And you can see that this disk then is going to get very hot because of the strength of the gravity of the black hole. and as a result, it will start emitting X-rays, which are emitted by objects that are, say, 10 to the power 6 or 10 to the power 7 degrees hot. And the black holes are such that the mass that is immediately surrounding them, just outside their Schwarzschild radius, will go to those temperatures. And that is why we get X-rays that will come out. It's the artist's impression of how a black hole, which is that little dot maybe, it can strip gas off its close neighbor and cause these accretion disks to form around them, which will be very hot. And so X-rays will be emitted by these black holes. And you can see such a system will emit these X-rays as they're coming out. They can get very, very hot. Now, even if you don't see the black hole, you can see these X-rays that are coming from the surroundings of the black hole. And these can be imaged by an X-ray telescope like Chandra, I just told you, and thus we can establish that these are black holes, because nothing else in the universe can make things so hot that they will emit X-rays other than neutron stars and black holes. And one can study these compact objects and the X-ray images of these objects and even figure out whether it's a black hole or a neutron star. And this has been done very routinely over the last 20 years, since X-ray telescopes like Chandra and the European XMM Newton went up. Here's an example of, for example, one of my own observations of the galaxy Centaurus A. This is an optical picture taken by a telescope on the Earth, a small telescope, which shows the stars in the galaxy. This is not a space-bound image from an X-ray telescope. This is normal light, and everything that you see here are normal stars that emit light that are seen by our eye. So these are stars that would be typically a few thousand degrees hot, and if things are 1,000 degrees hot, they emit optical light. And so like our sun is 6,000 degrees, and it emits yellow light. So these are lights that we can see with our eyes. But if you take the same area of the sky, the same galaxy, the same scale, and we observe this with the Chandra X-ray telescope for 1 million seconds, you get something like that. And here, everything that you see is more than 10 to the power 7 degrees hot, 10 million degrees hot. And this consists of a big jet that's coming out of the central supermassive black hole of the galaxy, which I'm going to talk about today. But all these point objects that are seen here are these binary stars that have either a neutron star or a black hole attracting mass from its companion and turning them into 10 to the power 7 degree plasma. In fact, we know that there are certain, we've modeled every single point object in this particular galaxy, and we know that, for example, that one, and there are various others which are actually black holes that are emitting X-rays, and some of the others are neutron stars. And you can do that by modeling the spectrum of the X-rays that are coming from it. So we can actually detect black holes from the X-rays. Now, this is not the only way we can find these black holes, and that brings us to the connection that we have with LIGO, and which is the underlying theme of this whole series of lectures. We know that in India we have these mega science projects that are coming in India, that India is becoming part of, and you know that one of them is LIGO-India, that is being built in India. And one of the major objectives of LIGO-India is to find black holes that already has been demonstrated is possible through other LIGO detectors. And what is that? And this is what LIGO-India is going to look like. And this we've already started working on it, and various other people in this series will tell you more about what's happening with LIGO-India. It is a collaboration with the LIGO observatories in the US, between the LIGO observatories and the Department of Atomic Energy and Science and Technology in India, and the the 4 institutes that are in charge of making LIGO-India are given here, and my institution, IUCAA, is one of them. Gravitational waves are a consequence of Einstein's way of looking at gravity. I told you that Einstein said that actually space-time is a fabric, and space-time is curved due to the matter, the mass of objects that are embedded in them. It also means that if objects move through space-time, it can create ripples in this space-time, which is also something that is not there in Newton's gravity. It is a consequence of the formulation of Einstein's way of looking at gravity. Now, when Einstein formulated this, he also worked out what these waves or ripples would look like, and he concluded that these would be really tiny ripples. Their amplitude would be so small that we'll never be able to observe them, he thought. And in 1916, he wrote a paper saying this will never be observed. And of course, as you know, 100 years after that, they were discovered in 2015. And in the discovery paper, which had 1,000 authors, up to 40 authors were from Indian institutions. In the discovery paper, very proud of being part of the gravitational wave phenomenon of the discovery of gravitational waves from the very beginning. And this has now become a big subject of research in this country, and we're going to build another LIGO here. This, of course, got the Nobel Prize 2 years ago as well. So this is the idea that the same thing that shows you that light can be bent and objects can be trapped around other objects in the universe due to the curvature of space-time also shows that, that as things go around each other in the universe, ripples can be created in space-time. This, of course, you've heard in previous talks, and you'll continue to see this idea of how LIGO works, how the gravitational wave detection process works throughout this series of lectures. So I'm not going to go into great detail to talk about them, but the idea is that as a gravitational wave proceeds through space-time, it causes the fabric of space-time to oscillate in very typical ways in which space is contracted in one direction and expanded in another. So the idea is that one would place an interferometer, which is very similar to a Michelson interferometer that physics students learn about in their undergraduate course, where laser beams bouncing off mirrors are in balance, producing fringes because they are identical in the two arms. And then what happens is that as the gravitational wave passes through the system, one of these arms would be deformed in a way that is different from the other. And as a result, the difference between the way the two arms respond to the passage of the gravitational wave will be detected. The idea is that this expected deformation is of the order of 10 to the power minus 18 meters, and this is what prompted, for 4-kilometer arms, that is, for if the detectors are much smaller, this would be even smaller, and this is what prompted Einstein to predict that this will never be observed. But the challenge was taken up by current astronomers and physicists, and this was done. How small is 10 to the minus 18 meters? If you look at progressively going from a meter down to a human hair to a wavelength of light, you can see that it is 1,000 times smaller than the diameter of a nucleus, and it is a marvel of physics that one has been able to actually detect deformations of the path of the laser light between the two mirrors by that amount in the LIGO instruments that now exist in across the US in two places. One is in Hanford in Washington State, and the other in Louisiana. These are the two places separated by 3,000 kilometers, which first detected the gravitational waves that were detected in 2015. And it turns out that they came from the merger of two black holes many billions light years away. Now, this system has now been joined by a third system called Virgo in Italy from the European Consortium, but in India, we are going to build the third of the LIGO observatories, and the work is now starting. The first detection in 2015, people might have shown this in earlier lectures, and you'll see more of this, came in the form of this, which came from the merger of two black holes. And the idea is that as two black holes that are of the order of the mass of the sun, it turns out they are, the first detection were black holes that were that were of the order of 30 times the mass of the sun. Each, as they merge together, they come closer and closer and closer, and the frequency of gravitational wave that comes out increases. This is the frequency as a function of time. And you can see that in a fraction of a second, in about a quarter of a second, the entire merger process happens, and the gravitational wave that is detected by these detectors saw a change in frequency in the typical way that this predicts. How large were these black holes? Anirban Ain, who was a student here in IUCAA, produced this amazing plot to show the Schwarzschild Radius of the black holes of the first system that was discovered, these were the sizes of whole states of India in its size in the Schwarzschild Radius. And it just gives you the idea of how large these black holes are. And if I don't know whether this will work, but if it works, it'll show you now of various black hole pairs that have now been discovered by the LIGO and Virgo collaboration. And I'll say this for about 2 minutes to show you the different kinds of black hole pairs and the resulting gravitational waves that have been discovered. And these are the various wonderful waveforms that you get from different kinds of black hole pairs. And the sizes of the black hole Schwarzschild radii are represented by the size of the balls that you can see. And you can see that the whole thing takes place sometimes a few seconds, and sometimes it's a fraction of a second. And these are, for example, this one was discovered in 2017, January. That is why the name of the event is given like that. And we have now more than 50 such events that have been. Not all of them are black hole pairs. Some of them are neutron star pairs. Some of them are pairs of black holes and neutron stars. But most of them that have been discovered are black holes. And some of them are pretty large compared to the others, and they start from a much larger distance than the others, and it takes a longer period to merge. And you can see the frequency of the wave as it increases slowly. The waveform becomes closer and closer together. These are some of the discoveries of 2017 in the second run of the LIGO, Virgo, together, working together. When Virgo, 2017 August, very productive for us, covering many of these. So what I would like to conclude this talk is to look at now the result of the two kinds of black holes that are discovered by the processes that I talked about. So in finding black holes from X-rays using an observatory like Chandra or XMM Newton, we find that we get black holes that are given by these purple dots here. And on the y-axis here is a number that gives you the mass of these black holes in terms of the mass of the sun. So for example, this black hole is say 35 or 36 times the mass of the sun. And you can see the most massive black hole that we found so far. So in this particular case, these two black holes have merged together to form this black hole, right? And so each event gives us 3 black holes, unless it is a merger between a black hole and a neutron star or 2 neutron stars. But these are all black holes that have been found by merging 2 black holes into a bigger black hole. And the most massive one is almost about 80 times the mass of the sun. This is not the most up-to-date plot. There have been discoveries since then, but you can also see that the ones that we have found from X-rays are of the order of a few times the mass of the sun. And Chandrasekhar said that you have to be at least 4 or 5 times the mass of the sun to turn into a black hole. And so these result from stars that are of that size. But certainly something like this has to come from a star that is very, very massive. The most massive star that we know of in our galaxy is 100 times the mass of the sun. So the fact that you can have black holes this massive was something that only LIGO gave us. You can see the basic difference between also the masses of the neutron stars that we found from the X-ray observations. You can see, and here is an example of 2 neutron stars merging to form a compact object that is come from LIGO. And these are in the yellow ones are all neutron stars that have been found from X-ray observations, like the ones from Chandra I showed you. And the qualitative nature just of the distribution of mass itself shows that we are learning completely new physics. These massive black holes and how they are formed is a topic of very active research now, because there are very big puzzles there. There aren't big enough stars in our galaxy that can give rise to some of these black holes, even after they explode. So we have to figure out how these black holes were formed. We also know that if there's a binary system in which in a massive black hole like this, say 20, 30, 40 solar mass black holes, the star explodes to form that black hole, it would be very hard to keep that binary system together so that the companion star would still exist to provide the mass that causes the X-rays to come out. So we know that we have to figure out how these binaries formed. It is possible that massive black holes form. They grow in mass by accreting more and more matter. And so these black holes could represent black holes that are not formed in the mass that you're seeing them now. It could have grown from where at the time they turned into a black hole. Also, the black hole the binary black holes that are formed, which merge to give out the gravitational waves, could have been formed from systems in which the 2 black holes captured each other after they had been formed separately in binary systems where they had a binary companion, which was a normal star. So these are completely new territory for us, for understanding how stars evolve, what happens to stars after they die. Clearly, the stars are not dying. They are being reborn as black holes that have a very active life. They can emit X-rays, bring in mass, grow in mass, and then they can capture other black holes and merge with them and create gravitational waves. And so we're looking at a cycle of the life of stars that we hadn't really looked at before. And the difference between the black holes that are seen from X-ray observatories and ones from gravitational wave observatories gives us this wonderful new hope that the LIGO detectors that are now being built, the gravitational wave detectors that are now built, there's one being built now in Japan, as you know, which is starting to observe right now, called CAGRA, and LIGO-India, which will be built now, will give a new idea of how stars behave towards the end of their life and even after they are done with their nuclear fusion. Of course, black holes are not the only things that gravitational wave detectors detect. There are lots of other things that other speakers will talk about. So here it is. This is what we want to build in India. starting to work from 2026, and I hope we start building soon after the shutdown is over. We are looking at life after the shutdown, and we will start building LIGO-India. And in 2026, we will have a network of the 2 LIGOs and a Virgo in Italy and LIGO-India here in Kagra in Japan, working together to detect these very, very interesting objects. We are on social media. Go look at us on Twitter and Facebook, and learn more about LIGO-India. And I leave you with a couple of books, if you're interested in black holes, that you can read to know about further knowledge about black holes. Thank you very much, and thank you for listening. Now, I know that a lot of I'm not looking at the YouTube feed that on which you have been listening to this talk, but I know that people have been asking questions and putting comments, and so I'm now being sent some of your questions, and I will try to answer them. If you would like to ask me any questions over the next few minutes, I'm here. You can write them as comments under the YouTube feed that you have been witnessing, and then I'll try to answer your questions. Okay, here I have the first question from Yuvraj Murali, who says that, can you explain how Einstein's equation predicted a black hole? Now, I told you that the way Einstein formulated gravity, it was not as a force between 2 objects that such that it is like something is pulling the other object to the string. The way Einstein formulated it is that there is an effect of the matter, the mass that is in an object, and locally the way it interacts with the space around it, and space itself is curved. And so, for example, if I can take you back to some of the slides I had, you can see that here, what happens is that the sun, or say a star, because it's massive, bends space-time around it, and as a result, anything that comes within the influence of the curvature of the space-time can go around, and because it's trapped around it. And all the planets here are trapped around. Mercury, which is very close, actually experiences very bent space-time, and it is completely trapped. And things that are very far away are not so trapped and actually can escape from it, right? So you can see that's how it goes. Now, what happens in this particular case is this is how Einstein's formulation of space-time works, is that just by the virtue of the mass of the black hole, which is the center, the space-time around it is curved so much that nothing can escape from it. And you can see that it goes right into a discontinuity in the middle, right? Almost it's infinitely curved. And it means that to climb out of it, you require an infinite amount of energy, and you require a velocity that is much, much larger than the speed of light. So even light cannot come out of this tunnel. So that is how Einstein's equations predict the existence of a black hole. Okay, so here is another question from Kundan Gupta, who says, is there any mass loss as the star turns into a black hole? Yes, of course. The idea is that as stars evolve, and then they uh, at the middle of the star where the nuclear fusion is going on, turning smaller elements, lighter elements into more massive elements. Then that particular process of nuclear fusion causes energy to be emitted by the star, and that we see as light from the star or different kinds of other kinds of energy. But in the end, all fuel is finished. So, for example, in 4.5 billion years or something like that, our sun will also finish its fuel, and then it will end its life as a star, which means its life as a light emitting or an energy emitting object. And once that happens, what happens to the star? There are various different kinds of things that happens to a star, and that is it starts losing mass because when it was generating light, there was a very delicate balance between the gravitation of the star and the pressure of the light and the thermal motion of the atoms, or particles, not really the atoms, but the atomic particles, the subatomic particles that are in the sun, in the star, that are moving around because of the thermal energy that is being emitted by this nuclear reaction. So once that nuclear reaction stops, then various effects happen throughout the star, and the catastrophic thing that happens is that the outer layers of the star explodes. Now, even before that, the star loses a lot of light and a lot of mass, because things, as you can see, when stars die, the outer layers are ejected, and you can see spectacular images of these things, like in the form of planetary nebulae, for example. And sorry, I do know I pressed the wrong thing here. Planetary, no, it's not what I wanted. Planetary nebulae, and it's not what I wanted. Planetary nebulae, and so it loses mass. So eventually, it's a central bit, the compact bit in the middle of the star, that collapses to form the compact object, the neutron star or the black hole. And that particular compact object has a mass that's much less than the original mass of the star, of the parent star, right? And so in the process of forming the black hole, the star does indeed lose matter. Now, that is why I was saying that to produce these 70, 80 solar mass stars, the star that gave rise to that, if it came from a single star, has to be much, much more massive. And we don't see that kind of massive stars in our galaxy right now. And so that is one of these very interesting things that astrophysicists have to solve now, is to how you get some of these very massive black holes. And one of the things we can see in these gravitational wave events is that we can see these black holes merging to form more massive black holes. So the 80 solar mass black hole came from a 30 and a 40 or a 50 solar mass black holes merging. Now that particular 50 solar mass black hole could have come from another pair, which is smaller mass merging. And so we actually directly are seeing in the LIGO events evidence that black holes merge to form bigger black holes. We have more questions. Diksha Adke has sent a question saying, how can machine learning contribute to the research of black holes? Of course, machine learning is a huge, huge tool that we are now using in various ways. For example, in the signals that we see from the merging objects as black holes merging signals in the gravitational wave detectors. What I did not show you, and what was shown by, for example, my previous speakers, Dr. Doravary and Dr. Mitra, showed you some instances where the actual signal that we get is embedded in a much, much bigger detection of various kinds of noise. Because as you know, you're measuring things that are displaced by 10 to the power minus 18 meters. if you just jump on your floor right now, you're going to cause displacements that are much bigger than that. And there are so many disturbances that are happening everywhere around the observatory that are much, 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 much bigger than that. So in order to find the correct signal of which comes from the gravitational waves, compared to the actual other things that are trying to distract you, is a big exercise. And there machine learning helps a lot, because algorithms can be trained to look for certain kinds of signals that we know from our modeling of what happens when stars merge. And as a result, that's one way of using machine learning. There are many other ways of using machine learning. For example, in IUCAA, one of our students developed a wonderful machine learning tool called Hey LIGO, which is a way of having something like Alexa or Siri look through large databases of logs of various things that have happened in gravitational wave observatories, very quickly accessing information, and to find the right information to troubleshoot these instruments. That's another very nice application of machine learning. And there are many, many others. In fact, within the LIGO scientific collaboration, there's a whole group that works on machine learning algorithms. And my institution here in Pune, IUCAA, is one of the major contributors to that. We have Siddhartha Chatterjee talking about why don't we choose the black hole which is situated at the center of our galaxy. Now, that's a very good question. I told you that I'm not going to talk about the supermassive black holes that are at the centers of galaxies, right? Because that is not the kinds of black holes that we can detect by our 4-kilometer-long LIGO detectors. These detect gravitational waves that are of the frequency range of about 1/10 of a hertz to 10 or even 100 hertz, that kind of gravitational waves. As you know, I showed you electromagnetic waves come in a whole range of frequencies. Gravitational waves also come in a whole range of frequencies. So just like you have optical light, X-rays, gamma rays, radio waves, millimeter waves in electromagnetic waves, in gravitational waves also you have the corresponding different range of frequencies. And this particular range of frequencies is what we can detect with the current LIGO design that we have, which are these arms of kilometer lengths. In order to detect gravitational waves from supermassive black holes, we need a completely different range of frequencies, which are not detected by these LIGO instruments. In fact, these are now being planned space-based interferometers, which will have much bigger effective arms than the ones that we can build on Earth. And to detect supermassive black holes, like the ones for which you saw in M87, the image formed by the Event Horizon Telescope, or the kinds of, so we can detect the black hole, the supermassive black hole at the middle of our galaxy by other means. We can detect them from the X-rays. I showed you a picture of the Chandra X-ray Observatory showing you the X-rays from the central black hole of Centaurus A. In the middle of our galaxy, we can detect the black hole through the dynamics of the stars around the central supermassive black hole. These are different things that I did not talk about today. But gravitational waves is not the way to find supermassive black holes right now. I can take another question, a couple of questions. There's a question from Ayush Sahu, which talks about what decides the orientation of LIGO detectors. That's very interesting because actually the orientation, a LIGO detector has two arms which are perpendicular to each other, right? And that's necessary, of course, because that's the geometry of the interferometer. But it also means that we can figure out roughly in the direction, not very well, but roughly the direction from which the gravitational wave is coming by the orientation of the observatory, because this, as I showed you, it causes contraction in one direction and expansion in the other direction, in the perpendicular direction. So by looking at and the way the gravitational waves arrival at two different places, we can figure out from what direction this gravitational wave is coming, but also the orientation of the two arms give us some idea of how of where this is coming. And so the Indian LIGO will have a different orientation, a slightly different orientation from the orientation that are in the LIGO detectors in the US, and that helps us in better characterizing from the form of the wave as to the parameters of the black holes that are causing the gravitational waves. There's another question from Arnav Das, which asks, do subatomic black holes exist? Micro black holes. What I said was, I mean, anything can be turned into a black hole, right? And so it depends whether you have a process in which you can squeeze a black hole into a size that will give you the Schwarzschild radius. Now, in principle, it is possible, but how would you do it is a question. As I said, I can turn myself into a black hole if I can find a squeezer that will squeeze me to atomic sizes. Now, if you take a subatomic particle or a microparticle, which is the size of an atom, the Schwarzschild radius for that, I mean, it's just proportional to mass. You can work it out. You can work out that the mass of the sun, which is 10 to the power 30 kilograms, if the Schwarzschild radius for that is 3 kilometers, you can figure out what a subatomic particle, which is 10 to the power minus 30 kilograms, what the size of it should be in terms of its Schwarzschild radius, right? And so it will be 10 to the power 60 times smaller than a kilometer. And if you can find a way of squeezing something to those sizes, then of course such a black hole exists. We cannot think of a way of doing it. And so we are not looking for them right now. I've got another question from Parag Kulkarni, and this will be the last question. We'll go off the air after this, and which says that we are a group of statisticians from Pune. How can we take active part in astronomically related data analysis? We are looking for statisticians to work with us. A lot of us can characterize the work that we do as statistics. In fact, we 2 years ago started a course called Astrostatistics in the Statistics MSc and Mathematics MSc program in Pune University. And we've been collaborating with the statistics department to teach astrostatistics, advanced statistics, machine learning, all kinds of things are used not only in gravitational wave physics, but in all kinds of astrophysics. So if you have an advanced statistical skill, if you're a group who wants to work on astrophysical problems, get in touch with us. You'll get our email addresses from the web and in various documents that are connected with this webcast. Contact us and we will see what we can do. Thank you very much for today's broadcast, and thank you for listening to me.